Welcome. In this video, we will explore the concept of SQL transactions, understanding their ACID properties, and how to control them effectively. We will learn how transactions ensure data integrity and reliability in database management. A transaction is a logical unit of work that contains one or more SQL statements. A transaction is atomic, meaning either all the statements within the transaction succeed, or none of them take effect. Imagine it as an all-or-nothing deal for your database operations. In the diagram, you can see that a transaction consists of multiple SQL statements such as insert, update, and delete. Depending on the success or failure of these statements, the transaction either results in a commit, which saves the changes, or a rollback, which discards the changes and reverts to the previous state. Here are the key commands to control transactions. The first is begin, which is used to start a new transaction. The second is commit, which is used to save changes permanently. The third is rollback, which is used to discard changes and revert to the previous state. The fourth is SAVEPOINT, which is used to create a point to roll back to. Here is an example of a basic transaction. First, we begin the transaction. Then we update the accounts table, setting the balance to balance minus 1000, where the account ID is 123. Next, we update the accounts table, setting the balance to balance plus 1000, where the account ID is 456. Finally, we commit the changes to save them, or we can roll back to cancel them. ACID properties are the fundamental guarantees of transaction processing in database systems. ACID is an acronym that stands for atomicity, consistency, isolation, and durability. Let's start with atomicity. All changes to data are performed as if they are a single operation. Either all the changes are performed or none of them are. Next up is consistency. Data is transformed from one valid state to another valid state. All database rules, constraints, and triggers are enforced. Continuing with the ACID properties, we will now discuss isolation. Transactions are executed in isolation from each other. The intermediate state of a transaction is invisible to other transactions. Finally, we have durability. Once a transaction is committed, its changes remain permanent even in the event of system failures, such as power outages or crashes. Here's an example of atomicity. Let's consider a bank transfer transaction. In a successful transaction, we begin the transaction. Then we update the accounts table, setting the balance to balance minus 1000, where the account ID is 101. Next, we update the accounts table, setting the balance to balance plus 1000, where the account ID is 202. Finally, we commit and all changes are saved. Before the transaction, account 101 has $5,000 and account 202 has $2,000. After the transaction, account 101 has $4,000 and account 202 has $3,000. In a failed transaction, we begin the transaction. Then we update the accounts table, setting the balance to balance minus 1000, where the account ID is 101. However, an error occurs here. The second update fails. Finally, we roll back and all changes are discarded. Because of the failure, account 101 still has $5,000, and account 202 still has $2,000. Notice that the transaction ensures that either both accounts are updated or neither is, maintaining atomicity. Transaction isolation levels control the degree to which transactions are isolated from one another. Different isolation levels address different concurrency issues, such as dirty reads, non-repeatable reads, and phantom reads. Read uncommitted is the lowest level of isolation, where dirty reads, non-repeatable reads, and phantom reads are all possible. Read committed prevents dirty reads, but still allows non-repeatable reads and phantom reads. Repeatable read prevents dirty reads and non-repeatable reads, but still allows phantom reads. Serializable is the highest level of isolation, preventing dirty reads, non-repeatable reads, and phantom reads. A dirty read occurs when a transaction reads data that has been modified by another transaction that has not yet been committed. A non-repeatable read occurs when a transaction rereads data it has previously read and finds that data has been modified by another transaction. A phantom read occurs when a transaction re-executes a query, returning a set of rows that satisfy a search condition, and finds that the set has changed due to another transaction. Higher isolation levels provide stronger data consistency, but may reduce concurrency performance. Let's illustrate isolation problems with an example of a dirty read. In transaction A, we begin the transaction. Then we update the products table, setting the price to 25 where the ID is 101. Then we roll back the transaction. In transaction B, we begin the transaction. Then we select the price from products where the ID is 101, and we read the price as 25. However, this is incorrect as transaction A rolls back, and the price should not be 25. We then process the order with the incorrect price. Finally, we commit the transaction. Dirty read transaction B reads uncommitted data, price equals 25, that was later rolled back by transaction A. This can lead to processing orders at incorrect prices, resulting in financial inconsistencies. This problem is prevented in all isolation levels except read uncommitted. Here is an example of a non-repeatable read. In transaction A, we begin the transaction. Then we select the price from products where the ID is 101, and we read the price as 20. Then we select the price from products where the ID is 101 again. Now we read the price as 22. Finally, we commit the transaction. In transaction B, we begin the transaction. Then we update the products table, setting the price to 22 where the ID is 101. Finally, we commit the transaction. Non-repeatable read transaction A reads the same data twice but gets different results because transaction B modified and committed the data between the reads. This problem is prevented in repeatable read and serializable isolation levels. Let's consider a phantom read example. In transaction A, we begin the transaction. Then we select all from products where the price is greater than 100, and we return 3 products. Then we select all from products where the price is greater than 100, and we now return 4 products. A phantom row appeared. Finally, we commit the transaction. In transaction B, we begin the transaction. Then we insert into products values 105 new gadget 150. Finally, we commit the transaction. Phantom read transaction A executes the same query twice and gets different sets of rows. Between the 2 executions, transaction B inserted a new row that matches the where condition of transaction A's query. The table contains the products 101, high-end laptop, price 1,200. 102 professional camera, price 800. 103 smartphone, price 600. 105 new gadget, price 150. Phantom reads are only prevented in the highest isolation level, serializable. This level uses range locks to prevent other transactions from adding rows that would match the condition of a query executed by a transaction that is still in progress. Here are some transaction best practices. First, keep transactions short. Minimize the duration of transactions to reduce lock contention and improve concurrency. Second, choose the appropriate isolation level. Balance data consistency requirements with performance needs. Use the lowest isolation level that meets your requirements. Third, error handling. Include proper error handling with rollback statements to maintain data integrity when errors occur. Fourth, batch operations. Group related operations into a single transaction to ensure atomicity, but avoid large transactions that span too many operations. Here's an example of a transaction with error handling. We begin try, then begin transaction. Then we withdraw from account 101 by updating accounts, setting balance equals balance minus 1,000 where account ID equals 101. Then we check if the balance is negative. If the balance from accounts where account ID equals 101 is less than 0, throw an error. Then we deposit to account 202 by updating accounts, setting balance equals balance plus 1,000 where account ID equals 202. Then we insert a transaction record. Finally, we commit the transaction. If an error occurs, we begin catch, roll back the transaction, log the error details, and insert into the error log. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.